Okay, this is exercise 2.8. We did miss this earlier on, but we're going back to it now. So exercise 2.8 further curve sketching. This is actually extension 1. So you were actually sketching curves like this earlier in the year, but now that we know about stationary points, inflections and inflections, you can actually add more details to your graphs. So earlier in the year, you were actually able to sketch graphs like this, but you just weren't able to indicate exactly where the maxima or the minima were or the inflections. However, you were indicating where asymptotes were, okay? So remember, when we sketch these, there's a few things that we need to do. We have to try and do y-intercepts, x-intercepts. We need to look for vertical and horizontal asymptotes as well. And we look at the behavior of the curve near any asymptotes. We also look for the value of the function, especially horizontal asymptotes, as x approaches positive infinity or negative infinity. What happens to the curve, okay? So I'm going to start with, remember that's just y equals x squared over x squared plus 4. I'm going to start with the y-intercept. So when x is 0, y, or your function of x, is 0 over 0 plus 4, which is just 0. So far we know that the curve passes through 0, 0. Now looking for any vertical asymptotes. So that's our y-intercept first. So first we did y-intercept, okay? Now for any vertical asymptotes, we need to look for vertical asymptotes. And for vertical asymptotes, that's where the denominator equals 0. But see, this will never equal 0. That's when x squared would equal negative 4, but that will never be the case. So therefore, we've got no vertical asymptotes. So what we're going to do now, we know the y-intercept. We know that the curve passes through 0, 0. We know that we've got no vertical asymptotes. Now let's, we will have horizontal asymptotes, but we can get onto that a little bit later. Well, I can do, yeah, we'll do that a little bit later. Let's look for stationary points and inflections. So f dash x for stationary points. Now we've got u and v. So before we do that, actually I'll just write down what my function is. Function of x is x squared over x squared plus 4. So u is x squared and u dash is 2x. V is x squared plus 4 and v dash is 2x. So therefore, f dash x, now this will be quotient rule because we've got a function divided by another function. So it's vu dash minus uv dash over v squared, which is v, that's x squared plus 4 times u dash, which is 2x, minus u is x squared times v dash is 2x over v squared is x squared plus 4 squared. Now let's just, what we can do, I wouldn't go factorizing this, I would just expand it, perhaps, or no, actually I might factorize it because then it'll be easier to solve later. So I've got two terms here, that term and this term. 2x is definitely a common factor, but there is no other common factor. So we've got 2x bracket x squared plus 4, that takes care of the first term. The second term, the x squared, is out, and then we're left with minus 2x. So just be careful there. My common factor is 2x, and when I take those out, I've got x squared plus 4 as my first term minus, sorry, made a mistake here, minus x squared there, okay? So 2x is my common factor. Take out my x squared plus 4, and I'm left with minus x squared there. So this actually, if I expanded it, it probably would have been quite nice, because if I just do that now, I realize I get some things cancelling. But if I just do it this way, I've got 2x times 4. Remember, I've still got my denominator, so I'm making a bit of a mess here, over x squared plus 4 squared. So, sorry, just a bit messy. So I've got 2x times x squared plus 4 minus x squared is just basically 2x times 4, which is 8x over x squared plus 4 squared. Now looking back over here, I probably could have expanded it, and I'll do that now. I've got 2x times x squared is 2x cubed, plus 2x times 4 is 8x, minus x squared times 2x is 2x cubed. And that is over x plus 4 squared. which means that I've got the same answer as here. I've got 8x over x plus x squared, sorry, over x squared plus 4 squared. Okay, so that's my first derivative. Sorry about that. So for stationary points, we've got the first derivative equals 0. So in other words, 8x over x squared plus 4 squared equals 0. Now, the only way that this is going to be equal 0, the numerator is not allowed to equal 0. So just the denominator has to equal 0, which means that x is 0. So therefore, I've got a stationary point at x is 0. Now, to determine the nature of the stationary point, we either can just substitute a value on either side, unless you want to differentiate this a second time. I particularly don't want to differentiate that a second time to do the second derivative. I mean, you can if you want. I think we should just look at the first derivative and look at points on either side of the first derivative. Remember, we're just looking at the gradient here. So we've got x is 0. There are no other stationary points. We might look at x is -1 and +1. So when x is 0, y dash, the gradient 0. When x is -1, we get 8 times -1 is -8 over, -1 squared is 1. So it's -8 over 1 plus 4, that's 5 squared. So it's -8 over 25. And over here, when x is 1, we get 8 over 5 squared. So it's 8 over 25. So what's happening here? We've got a negative gradient, a 0 gradient, and a positive gradient. So therefore, we have a minimum at when x is 0. Now we know that already when x is 0, y is 0. So we've got a minimum turning point. So we've got a minimum turning point at 0, 0. Now, so we've got a little bit of a picture of our curve so far. Okay, now I'm going to come up here and start sketching what we've got. We've got that the curve passes through 0, 0, and we've got a minimum at 0, 0. This is all we've got so far. Okay, that's all we've got. Minimum turning point at 0, 0, no vertical asymptotes. Y-intercept was 0, in other words, when x is 0, y is 0. Now we need to see if we've got any inflections. So you know what? We are probably going to have to do that second derivative. Let me just go back and look at the question again. And no, we do have to find the inflection. So off we go with the second derivative. So the second derivative. Now before I do that, I'll just write out my first derivative. So f dashed x is 8x over x squared plus 4 squared. So again, u is 8x. U dashed is 8. V is x squared plus 4 squared. And V dash is 2 bracket x squared plus 4 to the power of 1. Then differentiate what's inside, so times it by 2x. So V dash is 4x bracket x squared plus 4. Okay, so now let's do the second derivative. So I'm not going to have much room here. So f double dashed x is vu dash minus uv dash over v squared. So the second derivative is v, which is x squared plus 4 squared, times u dash is 8, minus u is 8x times v dash is 4x times x squared plus 4, over v squared is x squared plus 4 squared, and then square that again. So we've got, looks like a big mess, but I think we can just expand it rather than try and factorize terms. That's what I do. We've got 8, no, we're not going to expand it actually, because that's a squared. So we are going to factorize. So we've got 8 as a common factor, and we've got an x squared plus 4 as a common factor. And what's left over in the first term, we've got another x squared plus 4. And in the second term, we've got the 8. We're missing the 4 and these two x's. So we've got minus 4x squared. And we've got the x squared plus 4. See, we've got the 8 and the x squared plus 4 out the front. We're just missing the x and the 4 and the x. So it's minus 4x squared all over x squared plus 4 squared to the power of 2 is now to the power of 4. So we get 8 bracket x squared plus 4. Now this is x squared plus 4 minus 4x squared. That would be 4 minus 3x squared. over x squared plus 4 to the power of 4. Now that's what the second derivative is. Now remember, for inflections, second derivative is equal to 0. Sorry, this is getting quite long, okay? So I'm going to just go for another page. Just make sure we can still see what we're doing. Now, if you want, you know how we worked out that that stationary point at x equals 0 was a minimum. Now that I've done the second derivative, we can just check for the nature. When x is 0, what's your second derivative? F double dash x, or f double dash 0 is, I may as well just put it in since I've got it now. You get 8 times 0 plus 4 times 4 minus 0 over 0 plus 4 to the power of 4. That's substituting in, instead of check, I'll just write when x is 0, the second derivative, just working that out. Now that's 8 times 4 times 4. That's 16 times 8. Look, that is, I'm just trying to work out what that is. One sec. That's 128. 4 to the power of 4 is 4 squared. 16 times 16, I think it's 256. I think this equals a half, okay? Look, if it's, just check it on your calculator. I've just done it in my head, which is greater than 0, which is concave up. Therefore, we've got the minimum when x is 0. In other words, we've got the minimum at 0, 0. So I've shown this minimum 2 ways. Of course, you don't have to do it 2 ways. But looking back here, you probably didn't need to do this because with the first derivative, because we actually have to find the inflections anyway with the second derivative. So seeing as we were working out the second derivative, may as well just work out the type of stationary point that you've got. And then we better find any other inflections. So for any inflections, the second derivative is equal to 0. So let's just see what our second derivative is. And it's this. Okay, now, for that to equal 0, the numerator has to equal 0, not the denominator. So therefore, 8 bracket x squared plus 4 times 4 minus 3x squared is equal to 0. So therefore, x squared plus 4 equals 0, or 4 minus 3x squared equals 0. This obviously will never equal 0 because you get x squared is negative 4. That has no solution. But this, we've got 3x squared is 4. So x squared is 4 on 3, which means that x is plus or minus the square root of 4 on 3, which is 2 on root 3. So therefore, we've got possible inflections, and they occur when x is positive 2 over root 3 and negative 2 over root 3. So we better work out what they are. So when x is 2 over root 3, we have to substitute it into the original equation. We get y is 2 over root 3 squared over 2 over root 3 squared plus 4. Because remember, the equation is x squared over x squared plus 4. We get 4 over 3 divided by 4 over 3 plus 4. You can just do that on your calculator, or we can just do it manually. You get 4 over 3 divided by, now that's 4, that's 1 1/3, so you get 5 1/3, that's 16 on 3. Basically, you get a quarter if you work that out. So you get 4 over 3 times 3 over 16, which is 4 over 16, which is a quarter. So therefore, when x is 2 on root 3, y is a quarter. When you substitute x is negative 2 over root 3, you'll get the same answer because you're squaring the x term. So therefore, we've got possible inflections at 2 over root 3, a quarter, and negative 2 over root 3, a quarter, are possible inflections. This is getting quite long, okay? Now, we need to check whether they are inflections. So, checking concavity. So we've got x, f double dashed x. We know that there is a possible inflection at 2 on root 3, and that there is a possible inflection at negative 2 on root 3. So, let's start. 2 over root 3, just need to work out what that is approximately equal to. 3 is approximately 1.15. So I'm just going to look at when x is 1 and perhaps when x is 2. Okay, and over here that's negative 1.15. So I'm going to do negative 2 and negative 1. Okay, so again, looking at the second derivative, which is all the way up there. There it is. We have to substitute when x is 1. Now, I'm not going to work out the exact value. All I'm going to say is if x is 1, we've got 8 times, this will be positive because you've got 8 times 5 is 40. And then 4 minus 3 will be 1. So you've got 40 over 1 plus 4 is 5 to the power of 4. So you've got a positive over a positive. This is definitely positive, okay? We know second derivative equals 0 when x is 2 over root 3. And when x is 2, here we get 8 times 8, which is positive. And here we get 4 minus, now 3 times 4 is 12. You get 4 minus 12, that's negative. So you've got a negative. This will definitely be positive. So you've got a negative over a positive is negative. So therefore, you definitely have a concavity change. Now here, when you substitute these values into that, because they're all squared, you're going to get the same values for 2 and negative 2. So this one will be negative, this one will be 0, and this one will be positive. And you also have a concavity change. So I think we've got enough information now to do our graph. So what we've got, just going to start drawing it. We know that we had a minimum, going back to the question, we've got a minimum at 0, 0. All right, looking at the original question, there were no vertical asymptotes, and we had a minimum at 0, 0. And that was confirmed here as well, that we've got a minimum at 0, 0. So let's start drawing a minimum at 0, 0. But we know that if you look at these particular values, that we've got inflections at 2 over root 3. Now 2 over root 3 is approximately equal to 1.1. So also the curve was concave up when x was 1. So it's concave up, and when we hit 2 over root 3, we've got an inflection, and beyond 1.1 or 2 over root 3, the curve becomes concave down. So here is my inflection. See, we've got concave up when x is 1, which is about here. We know we've got this minimum, it makes sense. You've got the minimum at 0, 0. Concave up here, and then 2 on root 3 is the inflection. So therefore we've got the inflection at 2 on root 3, 1/4. And here we've got the inflection at negative 2 on root 3, 1/4. Okay? So we've got concave up here when x is 1, concave down when it's 2. Again here, when x is negative 1, concave up, then you hit that inflection and it goes concave down. So these are our inflections here. I've got an inflection at 2 over root 3, 1/4. Again here, I've got an inflection at negative 2 on root 3, 1/4. Now, the only thing that's missing is what happens to my curve. Now, it's concave down, it's coming like this. What happens to my curve as x gets quite large? Now, look, we can do this a couple of ways. We can do limit as x approaches infinity of the function. Here is my function. My function of x is x squared over x squared plus 4. I can do limit as x approaches infinity and divide numerator and denominator both by x squared and do that. Or I can just substitute large values of x. So when x is 10, I get function of x is, so just a large value of x. So when x is 10, function of x will be 100 over 104. You can just work out what that is and what it's approaching. I actually might do even a bigger value. When x is, say, 100, just go to your calculator and do 100 squared over 100 squared plus 4, and you're going to find that that is approaching 1, okay? That is like 10,000 over 10,004, and that is a little bit less than 1. So it's approaching 1, but from below, okay? So it looks like y is 1 is an asymptote. That's approximately equal to 1. You'll get the same answer when x is negative 100, because you square negative 100, you'll get positive 10,000 over 10,004, and that's approximately equal to 1, but it'll be slightly less than 1. It'll be about 0.99 something, okay? So when x is large negative numbers, you're approaching 1. So we need to write that this is the line y equals 1. And so that's our curve. So, you know, what curve sketching, what maxima and minima and inflections has enabled us to do is to know that the shape of the curve changes here. We were able to do this before, and we would have been able to do that as well, substituting in large and small values of x. But now we know we've definitely got a change in concavity here at 2 on root 3 a quarter and negative 2 on root 3 a quarter. We can even see the concavity of the curve by looking at the concavity of the curve around the inflection to know where it's concave up and where it's concave down. So it just gives us more of a picture of the curve when you're able to find inflections and turning points, okay, maxima and minima. So that's the end of that question, question 4, which is